Welcome to the section 3 of lecture 8. In this video, we will show the response of first-order systems to step change, impulse, and sinusoidal inputs. This slide summarizes the key characteristics of transfer functions. We saw this in section 1 video. First, the transfer functions are models in the Laplace domain expression that relate the process output to the input. Second, transfer functions are properties of a system or process. Transfer function depends on the differential equations that describe the process, but is independent from the input function. Third, they come from the physical process and include units that are necessary to relate the input to the output, but they do not describe the physical structure of the system. Fourth, they fully describe the dynamic system characteristics. Fifth, they are used to study the system or process output in response to various inputs to better understand the nature of the system. In the previous section, we introduced deviation variables to adjust the physical problem and simplify the initial conditions to be r equal to 0. And we introduced a fluid heater example where we used a dynamic lumped heat capacity analysis, which assumes uniform temperature over the sensor. The resulting transfer function for a temperature sensor was 1 over tau over S times 1 plus 1 over tau, which equals to ys over xs, also expressed as gs. Given this transfer function, we can calculate the response y over any input x. Let's start with the step change. We are going to make a positive a step that occurs at time 0. The Laplace domain expression is equation 6 in the table, which is a over s. After substituting x, we can get the response y to be a over s times 1 over tau over s times 1 plus 1 over tau. The next step is to find the partial fraction expansion. We get y equals a over s minus a over s plus 1 over tau. The details can be found in the course packet. By using equations 3, 6, and 15, we can use inverse Laplace transform to get the time domain solution yt equals a times 1 minus e to the power negative t over tau. The time domain equation describes how the deviation variable y responds with respect to time to a step change of a. This slide shows the normalized plot of the first-order response to step change. Another way to look at the figure is the first-order response to a unit step change versus time t over the time constant tau. When t equals tau, the response aligns with the vertical line where t over tau equals 1. When t equals 3 tau, the response aligns the vertical line where t over tau equals 3. This graph is classic because many systems are with first-order response. It's common to look at how they respond to a step change. When t over tau equals 1, 2, 3, 4, 5, yt goes from 0.63 to 0.86 at 2 tau to 0.993 at 5 tau. This table summarizes the y values at time t from 0 to 5 tau. Yt equals 1 minus e to the power negative t over tau. We can use the table or the graph from the previous slide to calculate the deviation variable response over time to a step change at different time points, as listed in this table. When t equals 3 tau, the response would have gone 0.95 times step change. In percentage, we can say that the process is 95% finished. So this is related to the response speed. When t equals 5 tau, the response would have completed 99.3%. We can also use this table to decide what time constant the sensor needs to have fast enough response. Let's say we need a sensor to behave as first-order system to reach 98.2% to the way to a step change input in 60 seconds. Based on this table, for first-order response to step change, we can see the response reaches 98.2% at 4 tau. So I can say 4 tau equals 60 seconds, which gives us tau equals 15 seconds, which means the sensor time constant tau must be equal to or smaller than 15 seconds. If the sensor has a higher time constant, that means the sensor is slower. It won't meet the required response speed. There are some other examples in the course packet. Let's get back to the first-order system response to different input functions. This slide shows impulse input, and the physical example is to add a bucket of something to a tank. The Laplace domain expression for impulse function is A. We substitute x in the transfer function to get this result, which is ys equals A times 1 over tau over s plus 1 over tau. We can invert it using equation 15 to get yt. Here is the normalized response of a first-order system to an impulse input function. It is exponential. The final function for this section is the sine function. Xt equals A times sine omega t. The result time-dependent equation is shown here. It shows the graph of both the input function of A times sine omega t and the response function yt. Input function is the solid line and the response function is the dashed line. There are a couple of things to know about the difference between the input function and the output function. First, the output function has an amplitude reduction. Input function goes from 48 to 52, and the output function goes from 49.2 to 50.8. So the output amplitude is less than half of the input amplitude. Secondly, the output function has a phase shift, which is almost 0.5 of the time unit after the input function. So the first-order response to a sine function has both magnitude, reduction, and delay. This brings us to the end of Lecture 8. Please write down any questions you might have and bring them to class. Thank you.